Assalamualaikum. For my part, which is the introduction, and soil classification in geotechnics is the cornerstone of understanding the diverse nature of soil beneath our feet. It's a systematic approach that categorizes soil based on their properties, aiding engineers and geologists in predicting soil behavior, determining suitability for construction, and devising appropriate engineering solutions. This classification involves analyzing various characteristics such as grain size, consistency, plasticity, and moisture content, providing a comprehensive framework for comprehending soil diversity and its implication in infrastructure development and land use planning. Different classification systems such as AASHTO, USGS, or British Soil Classification System categorize soil based on these properties, enabling engineers and geologists to communicate effectively about soil characteristics and make informed decisions in construction and land development projects. Understanding soil classification is essential because it forms the basis of soil characterization, allowing professionals to select appropriate construction techniques, mitigate potential risks, and ensure the long-term stability and safety of structures built upon or within the soil.
Assalamualaikum. For my part, which is application. Firstly, for AASHTO, which is American Association of State Highway and Transportation Officials, classification system is a vital tool in the field of highway transportation engineering. It plays a crucial role in evaluating and categorizing soils for road construction projects. By utilizing the AASHTO system, engineers can ensure the selection of soil that meet rigorous and stability and durability requirements, ultimately guaranteeing the long-term performance and safety transportation infrastructure. For the second part, the USCS, which is Unified Soil Classification System, offers versatility across various engineering applications. It classifies soils based on properties like particle size, plasticity, and moisture content, making it applicable in foundational construction, environmental assessment, and infrastructure development. The USCS system aids engineering and geologists in making informed decisions about foundation design, excavation techniques, slope stability, and environmental impacts related to soil behavior. Lastly, for the realm of agriculture and land management, the USDA, which is United States Department of Agriculture Classification System, holds paramount significance. This system provides valuable insight into soil fertility, texture, drainage, and suitability for different crops. By utilizing USDA classification, farmers, agronomists, and environmental scientists can make informed decisions about crop selection, implement efficient irrigation techniques, and plan land use strategies that optimize agricultural productivity while ensuring long-term soil health and sustainability.
We are required to review 15 case studies for this project. I'll present the first eight case studies and the rest will be presented by my groupmate Azrina. The first case study is about the development of mapping scheme between USCS and the USDA system. The research was conducted by Ruben A. Garsha-Gaines and Dr. Susan Frankenstein. The researchers used data from many resources to develop a good consensus method to map from one soil classification system to another. Next is the case study about Indian Standard Soil Classification System. The study mainly focused in comparing between ISSCS and the Unified Soil Classification System USCS in classifying fine-grained soil. ISSCS also used the similar plasticity chart that is used in USCS. But the difference is, in ISSCS, if the soil has liquid limit that is greater than 50%, the soil is classified as high plasticity. If the soil has liquid limit between 35% to 50%, the soil is classified as intermediate plasticity. And if the soil has liquid limit less than 35%, the soil is classified as low plasticity. However, in USCS, the soil is classified as high plasticity soil if the liquid limit is greater than 50% and low plasticity if the liquid limit is less than 50%. The third case study is about the on-site identification and classification system. The study explained the step-by-step guide on how to identify and classify soil in the field, starting by identifying the soil as coarse or fine-grained soil. If the soil is coarse-grained soil, the next step is to further categorize the soil as gravelly or sandy soil. If the soil is fine-grained soil, the test needed to be done to distinguish between silt and clay. Four simple tests that can be done to distinguish between the silt and clay are diluency test, dry strength test, toughness test, and dispersion test. The fourth one is classification of soil in civil engineering, written by Benjamin E. Beckers. In the study, he explains the significance of soil to civil engineers and the process of collecting soil samples in the field. He also discussed the visual and laboratory classification of soil for geotechnical purposes. In the study, he briefly explained the sieve analysis that is used for coarse-grained soil, hydrometer analysis for fine-grained soil, and the atomic test to determine the plasticity of the soil. Lastly, he described the AASHTO classification system, which is used for highway construction, and ASTM USCS, which is mainly used for engineering purposes. The fifth case study is about the sieve analysis and particle size analysis. The study explained the sieve analysis that is used to determine the grain size distribution for coarse-grained soil. The particle size distribution is represented on a semi-logarithmic plot of percent passing versus particle size. The author also provide an overview of the sieve analysis process, which started with sample preparation, followed by sieve setup, then sieving procedure, weighing and recording, and lastly plotting the particle size distribution curve. The sixth case study discussed the hydrometer analysis used to determine the distribution of fine-grained soil. The study includes explanation on why hydrometer analysis is used instead of sieve analysis. The author also explained the steps for soil hydrometer analysis, which includes all the required equipment, analysis procedures, the calibration of the hydrometer, and the calculations involved to determine the diameter of the soil particles being tested. The next case study is about the basic of soil classification for geotechnical engineering. The study described how soil is categorized using Modified Unified System (MUD) and USS. In the study, there's also a brief explanation about the soil classification of Occupational Safety and Health Administration (OSHA). OSHA classified the soil into three types: Type A, Type B, and Type C, based on the degree of safety for excavation. Type A soil is the safest for excavation, while Type C is the most risky for excavation. The last case study is about the soil classification categories for excavation according to OSHA. As mentioned earlier, OSHA classify the soil into three types: Type A, Type B, and Type C. But this case study give detailed description about the soil in each type. Type A soil has an unconfined compressive strength of at least 1.5 tons per square foot or 144 kilopascal. Type B soil has an unconfined compressive strength greater than 0.5 tons per square foot or 48 kilopascal, but less than 1.5 tons per square foot or 144 kilopascal. The last one, Type C, has an unconfined compressive strength of 0.5 tons per square foot or 48 kilopascal or less.
The next case study is about soil classification system, which is considered as a global language, and most geotechnical engineers are using this. Systematic and logical methods are suggested for classifying and characterizing the soils. The most widely used systems are USDAs, which defines soil based on defined content, AASHTO, which groups soils according to their usage as subgrade or embankment materials, and AS 1726993, which is mostly used in Australia. The 10th case study is about characteristics of soils, which consists of color, texture, and odor, as it helps manage fertility and successfully grow crops and ornamental plants. The size and proportion of these particles determine the soil's texture. Other than that, we also review about soil structure, which refers to the arrangement of soil particles forming aggregates of sand, silt, clay, and organic material, which can take various types of shapes. Examples of the shapes are granular, platy, blocky, columnar, and massive or single grain. The 12th case study reviews about attribute limits, which consists of 4 states such as solid, semi-solid, plastic, and liquid. All these states can be determined using methods of liquid limit, plastic limit, and shrink edge limit. In addition, the 13th case study discusses about 4 major components of soil, which are mineral matter, organic matter, soil air, and soil water. The system is constantly changing due to the presence of microorganisms and microorganisms, resulting in constant equilibrium. Next is sieve analysis of soil, which helps in determining the percentage of grain size in soil samples, producing a grain size distribution curve. Sieve analysis is used for soils larger than 0.075 mm in diameter, typically for sand and gravel. Last but not least is hydrometer analysis, used to estimate particle sizes from 0.075 mm sieve to 0.001 mm. To illustrate the particle size distribution, the data are presented on a semi-log plot of percentage water versus grain diameters. Hydrometer analysis is crucial for determining soil particle size distribution, which is essential for gradation curves and determining soil suitability for constructions. It can also predict soil water movement if permeability tests are unavailable.
Assalamu alaikum, Dr. My name is Mukhtar. I will present a discussion part. A key component of a soil science is soil classification, which provides a uniform method for grouping and describing soils according to different attributes. Numerous soil classification systems have been created throughout history, each with its own distinct criteria and methods. We looked at a few well-known systems in this report, including MIT, AASHTO, USDA, and the Unified Soil Classification, or USCS. Many characteristics of soil, including texture, structure, color, organic matter concentration, and mineral composition, are taken into account while classifying the soil. The numerous interactions between these components render the classification procedure intricate and dependent on throughout examination of soil parameters. Understanding this system is crucial for land use, agriculture, environmental governance, and also engineering or civil engineering. In buildings, it is also this classification is very important. However, challenges exist due to subjective evaluation and some soils not fitting existing classifications. Improving methods throughout technology like GIS and remote sensing and harmonizing international classification systems can enhance accuracy and communication. In essence, soil classification is vital or very important for understanding and managing areas. Soil is requiring ongoing research and collaboration to address limitations and meet modern needs.
As for the conclusion, the AASHTO, which is American Association of State Highway and Transportation Officials, USCS, which is Unified Soil Classification System, and USDA, United States Department of Agriculture Classification System, are 3 significant frameworks in soil classification. Each system offers a unique perspective on soil properties and behavior, catering to different industries and applications. For the AASHTO, it has 4 uses. First one is primarily used in transportation engineering. Second one is focuses on soil characteristic, and third one is used for highway engineering also. The fourth one is also enable professionals to make informed decisions regarding the construction and maintenance of roadway. The second one is USCS. USCS is globally recognized system that categorizes soil and used to detail description of soil properties that used to be applicable across engineering discipline. This can be held in construction with specific soil conditions such as dams. And for the last one is USDA. USDA is a classification system is specifically tailored for agriculture. It is focused on soil properties that affect crop growth and productivity. It has four factors. The first one is soil texture, structure, permeability, and facility. These all are considered in these systems. Farmers can also inform the decision about the soil. That's it for the conclusion.